Our universe is full of wonders, stretching far beyond what the eye can see. From the vast expanse of space to the tiniest particles, there's always something that sparks curiosity and ignites the imagination. One such realm that has captivated scientists and the public alike is the quantum world, a domain that defies our everyday experiences. This is the world of atoms and the particles within them, a place where the very fabric of reality is woven. It's a place where the rules of classical physics, the physics of our everyday experience, no longer apply, and new bizarre rules take over. Imagine a world where things can be in two places at once, a phenomenon known as superposition. Picture a reality where particles behave like waves, a concept that challenges our very perception of matter. This is the strange and fascinating realm of quantum mechanics, a field that continues to baffle and intrigue scientists. It's a world that challenges our intuition and forces us to rethink our understanding of the universe, pushing the boundaries of what we know. The quantum world is not some distant, abstract concept. It's a tangible reality that we are beginning to harness. It underpins our very existence, influencing everything from the smallest cells in our bodies to the vast cosmos. The devices we use every day, from smartphones to lasers, are all built on the principles of quantum mechanics, showcasing its practical applications. Join me on this journey as we delve into the quantum realm, exploring the mysteries and marvels that lie within. Quantum theory is a branch of physics that describes the behavior of matter and energy at the atomic and subatomic levels. It delves into the very fabric of reality, exploring the smallest building blocks of the universe. It's a revolutionary framework that has fundamentally changed our understanding of the universe. Before quantum theory, classical physics was our main tool, but it couldn't explain phenomena at the microscopic scale. One of the key principles of quantum theory is wave-particle duality. This principle challenges our conventional notions of particles and waves. This principle states that particles, like electrons, can exhibit both wave-like and particle-like properties. For instance, electrons can create interference patterns like waves, but also collide like particles. This is a concept that's difficult to grasp intuitively because we're used to objects being either waves or particles, not both. Our everyday experiences don't prepare us for such duality. Another important concept is quantum superposition. This idea is even more mind-bending. It suggests that a particle can exist in multiple states at once until it is measured. This means a particle can be in different places or states simultaneously. Imagine a coin spinning in the air. While it's spinning, it represents multiple possibilities. It's not heads or tails until it lands. Only then does it choose a definite state. Similarly, a quantum particle exists in a superposition of states until a measurement is made. The act of measurement forces the particle to choose a state. Quantum theory also introduces the idea of quantum entanglement. This is one of the most intriguing and mysterious aspects of quantum mechanics. This is a strange phenomenon where two entangled particles can influence each other instantaneously, even if they are separated by vast distances. Changes to one particle affect the other, no matter how far apart they are. It's as if they are connected by an invisible thread that transcends space and time. This connection defies our classical understanding of the universe and suggests a deeper, more interconnected reality. At the turn of the 20th century, a German physicist named Max Planck ignited a revolution in science. His groundbreaking work laid the foundation for quantum theory and earned him the title of the father of quantum physics. Planck's journey into the quantum world began with a seemingly simple problem: understanding the radiation emitted by heated objects. Classical physics failed to explain the observed patterns of this radiation, known as blackbody radiation. In 1900, Planck proposed a radical solution. He suggested that energy, unlike a continuous flow of water, is emitted in discrete packets, or quanta. This revolutionary idea challenged the prevailing view of energy and marked the birth of quantum theory. Planck's discovery was met with skepticism initially. It was a radical departure from classical physics. However, his work soon gained recognition as experimental evidence began to support his theory. Section 4. Planck's constant, a quantum revolution. Planck's revolutionary idea of quantized energy was not just a theoretical concept. He went further and introduced a fundamental constant that would forever change the landscape of physics: Planck's constant, denoted by the letter h. This constant relates the energy of a photon, the quantum of light, to its frequency. It's a tiny number, but its implications are profound. It tells us that energy is not continuous, but comes in discrete packets, or quanta. Planck's constant became a cornerstone of quantum theory. It paved the way for understanding the behavior of atoms and the interactions between light and matter. It's a testament to Planck's genius that his work continues to shape our understanding of the universe over a century later. Section 5. The Quantum Timeline, a journey through discoveries. The development of quantum theory was not a solitary event, but a series of groundbreaking discoveries that unfolded over several decades. It was a collaborative effort involving many brilliant minds, each contributing a piece to the puzzle that would eventually form our understanding of the quantum world. Let's take a journey through time to explore some of the key milestones in this quantum revolution, a revolution that has fundamentally changed our understanding of the universe at the smallest scales. In 1900, Max Planck proposes that energy is quantized, marking the birth of quantum theory. This radical idea suggested that energy is not continuous but comes in discrete packets called quanta. In 1905, Albert Einstein explains the photoelectric effect using Planck's quantum hypothesis, further solidifying the idea of quantized energy. Einstein's work demonstrated that light itself is quantized, behaving both as a wave and as a stream of particles called photons. In 1913, Niels Bohr proposes his model of the atom, incorporating quantum principles to explain the stability of atoms and the discrete nature of atomic spectra. Bohr's model was revolutionary, showing that electrons orbit the nucleus in specific quantized orbits. In 1924, Louis de Broglie introduces the concept of wave-particle duality, suggesting that particles can exhibit wave-like properties. This idea was groundbreaking, proposing that matter has both particle and wave characteristics. In 1925 to 1926, Erwin Schrödinger develops wave mechanics, and Werner Heisenberg formulates matrix mechanics, both providing mathematical frameworks for quantum theory. These two approaches, though seemingly different, were later found to be equivalent and complementary. In 1927, the Copenhagen interpretation of quantum mechanics emerges, emphasizing the probabilistic nature of quantum measurements and the role of the observer. This interpretation suggested that particles exist in a state of probability until they are observed. These are just a few of the key milestones in the development of quantum theory.
Each discovery built upon the previous ones, creating a tapestry of knowledge that continues to evolve. The journey continues today as scientists delve deeper into the quantum realm, unraveling its mysteries and exploring its potential.
From quantum computing to quantum cryptography, the applications of quantum theory are vast and hold the promise of revolutionizing technology and our understanding of the universe.